everyone, and welcome to the Black Hole. Today, very pleased to have with us Mansoor Ahmad, which I was reading from his CV today, is also commonly known as Mooney. So he is now scientist emeritus at NASA. He has been with NASA for a very long time, for the longest span of your career, I guess, and he's from Peshawar, grew up there, went to the US in the 70s and obtained degrees in mechanical engineering from the University of Maryland and George Washington University. He has also been the Associate Director for the Astrophysics Division at NASA. Important projects that he has been involved in are the Hubble Space Telescope and LISA, which is the Laser Interferometer Space Antenna, which you might know was involved in the detection of gravitational waves. Um, Further, he has been the Deputy Project Manager of the James Webb Telescope, and this is what he's going to talk to us about today. He has been the recipient of several prestigious awards, including the Goddard Space Center Achievement Award and the NASA Group Achievement Award. But apart from all of that, he's an avid filmmaker, and he has made some 20 films, and we're hoping we'll be able to show some of them here at the Black Hole as well.
Thank you very much, ladies and gentlemen, for finding time this evening to listen to me. But first of all, I'd like to thank Dr. Sadia and Mr. Pervez Bhutbhai for allowing me to come and talk to you guys. I'm a great fan of Pervez Saab, so I find it a great honor for me to be able to come and join him in this endeavor of getting all of you together for the sake of science and literature and philosophy, I guess. Today's topic is we'll talk about the James Webb Space Telescope. So James Webb Space Telescope is the latest achievement that NASA has been proud of in the astrophysics area. Before that, Hubble was the you can go back to the first slide. Hubble was the pride and joy for NASA. Everybody, I'm sure, is aware of the scientific achievements that Hubble has been producing over the last 32 years. And it has produced amazing science, but it also created new mysteries for us to solve. So the James Webb is the latest achievement, which is far exceeds the complexity, not in the science, but also in the engineering of building this machine, by far from what we had to go through for Hubble. So we'll talk about some of those. But let's see, where does the story for James Webb start? So I think the story for James Webb starts thousands of years ago, when the humans became knowledgeable enough, shaur, to look up in the sky and start getting amazed by what they saw. And ever since then, they have observed the stars. I think that was the very first what you call remote sensing activity that humans ever endured upon, and that is to observe things in the distance, evaluate them, and make some conclusions about what they're seeing and what the universe is like. And then, as they grew more and more intelligent, they started to use that knowledge for human activities. They used the stars for navigation. They figured out the Earth is not flat, it's round. The sun is rotating around the Earth. And as the technology grew, got more and more technically advanced, Galileo discovered the telescope. We got to know even more. And so over the centuries, we have come to know more and more about our universe. And to, again, get more deeper understanding, we need bigger and bigger instruments to observe the universe. And so Hubble was the last one. There was a very powerful telescope, but it had its limitations. And so the James Webb Telescope was desired by the scientists. And we'll go over why all of that was. So the question is, why are we building these machines? Not just for the hell of it, but because there are some scientific questions, let's say in astrophysics, that we still are trying to answer. And so to answer those questions, we need to keep advancing our technologies so that we can peer deeper and deeper into the universe. So before we get into the details of James Webb, I'd like to start with a 10-minute video that gives you an overview of the whole project, of what the science goals are for the Hubble, for the James Webb Space Telescope, and what are the engineering challenges that were caused by it. So you'll have a good overview of what we're going to talk about for the next hour or so.
This is a science mission on par with Apollo missions, Space Shuttle, International Space Station, and Hubble missions. For nearly 2 decades, thousands of people around the world, many spending their entire careers, built the James Webb Space Telescope. And it all comes down to this.
Once we launch the James Webb Space Telescope, there are no second chances. We have 300 single-point failure items, and they all have to work right. When you're 1 million miles away from the Earth, you can't send someone to fix it.
We've never put a telescope this large in space. We want to see distant parts of the universe humans have never seen before. Looking back in time, almost 14 billion years, to see the first galaxies that formed after the Big Bang. And we want to search for the building blocks of life in the atmospheres of planets orbiting distant stars. To unfold the history of the universe, we must first unfold this telescope.
This is the largest primary mirror, the largest sun shield, and the most powerful space telescope ever built. And yet, this large telescope needs to fit inside a 5.4 meter diameter rocket fairing. That's the largest fairing size available on any rocket, and it's the fairing size on our ride to space. The Ariane 5, provided by the European Space Agency, is one of the world's most powerful rockets. To cheat the fairing size limit, we built Webb to fold, like origami, to fit inside the rocket fairing.
And this brings us to our most challenging part of this mission, unfolding it in space.
This, thank God.
Think of what you're doing. You're taking this extraordinarily delicate, precise, state
James Webb was launched, so you could see all the tension and concerns that everybody had. But I'm happy to report that James Webb has been launched. It was launched December 25th. It has finally reached its orbit successfully. All the deployments have gone very smoothly, and finally the mirror adjustments have all been done, and it's taken its very first test image. So we'll talk about some of those in more detail. So we're very happy that everything has worked as planned, and that goes to show the engineering prowess that NASA had to go through to build this machine and make sure that everything worked. So quickly, the outline for my talk. We'll start with what are the major astrophysics questions that we are still trying to answer, and therefore we need these machines to answer those questions. But then you might say, why do we need telescopes in space to begin with? We can have telescopes on the ground. We can make them as big as we want. So what's the advantage of having a telescope in space? So we'll talk about that. We'll talk about Hubble. What has Hubble done and what's its limitations, and why do we need another telescope that's bigger than Hubble in the name of James Webb? And we'll go into what are the science drivers that James Webb needs to do that drive the technical challenges that we as engineers and managers had to figure out how to solve to build this machine. And then we'll go from there. What are the big astrophysics questions nowadays? Next slide. How does the universe work? What's the role of black holes? How are the stars born and die? What are the nebulas? What are the galaxies? Why are the galaxies the way they are? Next slide. How did the universe evolve from the Big Bang to what it looks like today? If you look at the universe, it's a simulation of what the universe looks like. It is very blotchy, with some channels connecting the various regions. But if you go back to Big Bang and think about Big Bang, it was a huge explosion. You would expect that the matter would have been ejected uniformly all around. And so you would expect that the universe would be pretty uniform everywhere you look. But now that we look at the universe, it's not that. It's very chunky. Even though in the night sky, we see the stars, but if you zoom back out of our solar system and look at the stars, you see that a lot of stars are kind of clumped together in neighborhoods. And then when you zoom further back, you'll see all those stars are actually living in a galaxy together. And then there are wide open spaces, and then there are another galaxy. If you further zoom back, you will see that they're neighborhoods of galaxies together. So it's very, very clumpy and chunky. So what has happened? How has the universe evolved from the Big Bang to what it is today? Coming back to the next slide, more interesting questions. Where did we come from? Again, think of the Big Bang. Big Bang, the very first few seconds, all we had was a very elementary subatomic particles, building blocks of atoms. And then soon after that, those particles combined together to make a proton and a neutron and electrons, and you got ionized hydrogen basically, which is the simplest element in the periodic table because it only has one proton. And then of course the electron got captured and you got neutral hydrogen, but that's the simplest element that could possibly exist at that time. But you look at it today, what are we made of? You know, we are made of carbon, we have iron, we need oxygen. So if you look at those atoms, they are very, very heavy atoms. Each of them have multiple protons in them. And so how did the hydrogen atoms gain protons to make the next element? And we know that the only way you can put another proton into an atom is by fusing another proton into an atom, which takes a hell of a lot of energy or some kind of force that can push those protons together. So from one proton to the multiple proton elements that we have today, how did they come about? Because if they hadn't, we wouldn't be here today. So that's an interesting question. Next slide. I think that's the most interesting question. That is, I'm sure everybody has thought about it at one time or the other. Are we alone in this universe, or are there other beings somewhere else in the universe? Whether or not they're intelligent or they're just microbial, are they there, or are we the only ones? The answer to that question, either way, is a very profound answer in my mind. Either we are the only one in this huge universe, and so we are very, very special, or that we're not that special, and there are other life forms in the universe, perhaps even more intelligent than us. And so how do we look for them? How do we find them if they are there? The easiest way would be that if one of them shows up in our neighborhood, park their flying saucer in our backyard and say, hello, I'm such and such, come from planet blah blah. That's the only way we will know for sure that they are here. Things are very far away in the universe from us. Our closest, we have looked at our own solar system that we know for sure there's no sign of life, at least an intelligent life, in any of our planets. The next star from us is four light years away. And so, by the technology that we have, even if there was life that we would go to look for it, the technology of traveling in space, it will take probably thousands of years for anyone else and us to go there and see if there's life form here. So all we have is, again, relying back to remote sensing. Can we detect light remotely while sitting on Earth? What do we need to observe in the universe to detect if there's any life? So we'll talk about that a little bit. Next slide. So the last 10 or 15 years or so, the new mystery has come out, which we're calling dark energy. Of course, dark matter had been discovered very long time ago. So there's evidence of there's a matter that exists in the universe without which we could not explain the behavior of the universe, but we know it exists, but we have no clue what it is. And we're still searching for some clues, and so once you don't know anything, we just put a word dark in front of it. So you say, okay, there's some dark matter, and then since Hubble was launched, we discovered, Hubble was launched to answer one of the questions it was supposed to answer is, what's the fate of the universe? After the Big Bang, there's an explosion. Like if you throw a ball up in the air, because of the gravity, the ball will come back. So the Big Bang explosion, depending on what the mass of the system is there enough gravity in the system that it will slow it down and pull it back again to a big crunch and have another Big Bang? And if that's the case, is ours the first Big Bang, or is it the 20th Big Bang? We don't know. If there's not enough matter, if there's not enough gravity, the universe will continue to expand. It'll cool down and eventually cool off and die. So to answer that question, we needed to figure out what the Hubble constant, or the mass of the total mass or the gravity in the universe is. But instead of answering that question, Hubble discovered that even though the universe was expanding for several billion years, but last 6 or so billion years ago, it started to accelerate. It started to go faster. It started to expand faster than it was before. So I don't know if all of you have studied physics or not, but Newton's first law of motion says that if a thing is moving at a uniform velocity, it only can do that if no force is acting on it. But if it's accelerating, it's going faster, then there has to be a force that's causing that acceleration. So if the universe has started to accelerate, there must be a force or an energy that has somehow appeared that we didn't know about that's causing the universe to expand faster. So we, again, don't know what that is. So we call that dark energy. So these are some of the major questions that we're trying to answer. And that's why we're building bigger and bigger machines, different kinds of machines to study the universe from a different perspective. Next slide. So like I said, humans been observing the universe for centuries, but until very recently, we've been relying on what we observe with our own eyes. And we're recognizing now that our eyes are of very limited, optimized for very limited a band of electromagnetic wavelengths that exist in the universe. The top curve shows the whole range of the electromagnetic radiation that's coming out from different objects in the universe, anywhere from very long radio waves to microwaves to all the way to gamma rays. We are only seeing a small band in the visible light with human eyes. So you can say that we have blinders on, we can only see what we are built to see, and therefore we have no knowledge of what other wavelengths are carrying in terms of the information. So if you could look at the universe with those eyes, we can probably put more things together and probably get a better understanding of what the universe looks like. The problem, or actually the good thing about our atmosphere, is that it doesn't allow some of those very harmful radiations to come through and protect us, which is good. But it also means that we cannot observe those wavelengths from the ground because they're not accessible to us. Also, if you were to look deeper and deeper into space, you can imagine the farther things are, more dimmer they will be. You know, if you take a bulb and start moving farther and farther, it'll get dimmer and dimmer and dimmer. And if you take a picture of that bulb that's very, very far away, if you know anything about photography a little bit, what you have to do is take the biggest aperture, open up the aperture of your camera to as large as you can, keep the camera very stable so it doesn't move, so that it can collect as many photons over a long period of time, and it will eventually give you a sharp image. So another problem with our atmosphere, it doesn't have a very constant density. So because of the heat, temperature variations across the height of the atmosphere, the density is very varying. So as the light from a very, very distant object comes through, the image moves. This is what we call, you know, the kids know the twinkle, twinkle, little star, right? You've heard that? That sounds great for a nursery rhyme, but it's a pain in the neck for astronomers because they cannot take pictures of very, very deep objects staying on the ground. Of course, now the technology has evolved where we can actually adjust the optics to account for the twinkling of the stars. But because of that atmosphere, that's another reason why it's important to have telescopes above our atmosphere. So this picture kind of shows the various telescopes that we have built that are optimized for different wavelengths. So some of these Planck, Herschel, and all are very large, long wavelength microwaves, infrared, Hubble, of course, in the visible, and of course, X-rays, gamma rays, and so forth. And James Webb is now being built with the optimization to be able to see infrared light, and we'll talk about that, why that is. Next slide. So this is what we know so far about the history of our universe. So we had a big bang, and a very few microseconds, and even smaller than microseconds later, the universe really expanded very fast, faster than the speed of light, and it cooled down. So that's when the hydrogen atoms started to form. The light that was there from the initial Big Bang disappeared because there was nothing to light it anymore. They were just atoms. They didn't produce any light. And so the universe went into what we call a dark age. So there was no light for 400 million years. This is how long it took for those hydrogen atoms to start colliding together to make a bigger mass. And as you know, rolling ball gains mass. If you roll a ball in snow, it gets bigger and bigger. So that hydrogen atom started to get bigger and bigger and started to collect more and more mass. And over 400 million years later, it became so huge, that mass, that the gravity force of that mass that was exerted into the center of that mass pushed the two protons of hydrogens together and created the fusion reaction and created the energy equal delta E equals mc square. So the mass combined it with slightly less mass in the end, but the rest was energy. So that's how the fusion works. You put enough force into the atoms to put more protons in it, and so the star started to burn. That's where the light start coming out of the universe. And of course, that energy started to balance out the gravitational force. The gravity would tend to pull you in, the energy will try to push you out, and the star became into equilibrium and started to shine. And so 400 years later, the first light appeared in the universe. We'll talk more about what happens to that star, but what happened here is the hydrogen became fused and started to make the next element in the periodic table. So we had the first light coming out 400 million years after, and then from there we can see how the universe started getting clumpier and clumpier and started to expand, and then a few billion years ago it started to accelerate. Next slide. So you may say, how do we know about this? How do we know what happened, 13 billion years ago? How can we look in the past? So that has to do with speed of light and the distances that we are dealing with. So let's look at the moon. Moon is, light years is a measure of distance, right? So it's how far light can travel in that year of time. So moon is 1.3 seconds away from Earth. So when you're looking at the moon, you're looking at it 1.3 seconds ago. The sun is 8 minutes away. So when you're looking at the sun now, it was really not there now, it was there 8 minutes ago. Same as Neptune, 4 hours. Neptune is 4 hours away. And like I said, the closest next star to us is 4 light years away. Let's say that you had a relative there, and he takes a picture of himself and emails it to you, to Earth. And of course, let's say that that email comes at the speed of light, so it takes 4 years for that picture to come to you. So when you're looking at that picture, your relative is not that person anymore, it's 4 years older. So you extrapolate that. If you're looking at things farther and farther away, you're looking at the light or the picture of that image as it left that long ago. So this is what Hubble has done. We take a snapshot of galaxies nearby, and we can tell how far those galaxies are. So you can see how far back in time you're looking at and what they look like. So as you go farther and farther and farther, you can see this light has taken maybe 11 billion years to reach us. So what we're looking at it now is what it used to be 11 billion years ago. So now we know the history of the universe that looked like 11 billion years ago. And so that's how you figure out the history of the universe. The other thing you noticed is that as you go deeper and deeper, and that means farther and farther away, the colors of the galaxy have started to turn into red. And we'll talk about that in a minute. And that's where the limitations of Hubble start to show up. Next slide. And that has to do with Doppler Effect. Again, some of you who are not familiar with physics, you probably are ever been into a train station or standing on the road, and a car's coming by, it's beeping his horn, and it's coming towards you. The horn sounds high pitch, and it goes by you, it goes high pitch. That's because as the sound is coming to you and the car is coming to you, it's compressing its frequency of that sound that's coming to you, and so the sound is coming faster and faster, and so it looks like it's at a higher frequency as it's approaching you. And as it goes by you, each sound that's emitted is coming later and later, and so the frequency is getting longer and longer, and so it sounds like it's a high pitch. What we know about our universe is that universe is expanding, therefore everything is moving away from everything else. And farther the galaxies are, the faster they're moving away from us. So the Doppler shift is taking effect even in light. So as the light may be emitted and visible from this distant galaxy, but as it's moving away, by the time we detect that light, it's turned into infrared. And Hubble, like I said, is optimized for visible light. It has a very tiny sensor in near infrared, but mostly visible and a very little in the UV. So at some point, we believe that Hubble is no longer able to see beyond certain distance, because even though the galaxies may be there, we just cannot detect the light. Next slide. So this is a very famous Hubble deep field image. We pointed Hubble to a very ordinary dark portion of the very tiny sky, maybe the size of looking through a straw. And we said, okay, if there are things that are so fine that we cannot really see it, so let's do that photography trick. Open up the aperture, let it stare at the spot for 11 days and see what we get. And after 11 days, it collected this image. And in this image, each and every point of light is a galaxy by itself. It's a galaxy made out of trillions and trillions of stars. And that's just in this little tiny portion of the sky. So just extrapolate that all around 360 degrees to give you an idea of how vast the universe is. But you're also noticing, again, the colors are changing. The closer galaxies are bluer, the distant galaxies are red. Next slide. And so we believe that there, even though we see dark areas, we can't be sure that there is nothing there. We believe that there are older galaxies that are emitting light, but they're in infrared, so Hubble cannot see it. Next slide. So we believe the light is there, it's coming to us, but we haven't yet seen it, even with Hubble. So that's where the need for an infrared telescope comes to be. Next slide. The other thing that Hubble is limited because it doesn't have infrared is that, like I said, the stars was born and it started to fuse. The very first generation stars were fusing hydrogen. And at one point, after maybe a few billion years, depending on how big the star is, that fuel eventually exhausted, right? It used up all the hydrogen that it had. And so if the size of the star was only big enough to create enough gravity to fuse just a single proton together, it didn't have enough power to fuse the next generation, the two protons and two protons into 4 protons. The energy stops. It cannot hold the gravity force anymore. And so the gravity pushes all the matter that it has created towards its core. And since the core is now very hard, it hits the core, bounces back out, and it gets ejected all over into space. And the same process starts again. That dust that has a higher next generation elements in it starts to gather mass, starts getting in bigger and bigger. Now it has to get much bigger to start fusing the next element. And so in the throes and the death throes of a star, new stars are born, but they're born in the middle of the dust. And so dust doesn't let the light come through as easily. So Hubble cannot really study the births of stars that are happening inside the nebulas and the dust clouds of other stars very well. So that's another reason why we need, can you go back? Infrared light. So in this picture, we have the same picture, one taken with visible light, one with infrared. And you can see through this opaque object, the hand of the person, because the infrared light is produced because of the temperature. And so the hand is probably warmer than the trash bag it has. So infrared machine could probably penetrate through the dust clouds and observe how the new stars are being born. We'll talk a little bit more about that. Next slide. So this again, like I said, using Hubble's limited near-infrared capability. This is a picture of dust clouds. We call it fondly the pillars of creation, that a star has exploded and it has ejected its matter. But you can see some glow either coming from these clouds or around the clouds. So we believe there may be something either in these clouds or behind the clouds that are causing this light. But when you use the near-infrared light, next slide, you can really see through that all of these hundreds of new stars are being born inside the dust cloud. And so that's another reason why the scientists decided that we do need another telescope that is optimized in infrared light. Next slide. So that's how the James Webb requirements came to be. The scientists said, we need something like Hubble and optimized in infrared light, but just the size of Hubble is not enough. We need much bigger mirror. So we negotiated them to a 6.5 meter. We'll talk more about the issues with that. So that's what James Webb looks like now. Next slide. And we hope that with its capability in infrared, we can see all the way back to when the very first stars were born, when the dark ages ended. And that's why we used to call it fondly the first light machine. And we're pretty sure that now that the mirror has been tested and everything, that it is going to meet all the requirements that it's been asked to. So we hope that it'll be able to actually see the very first light that came into the universe. So what are the scientific goals for James Webb? Detect the end of the dark age, look at the assemblies of galaxies as the galaxies evolved from the early universe to now. Scientists believe that the galaxies were much smaller then, and they became bigger because they started to merge together and collide together to get bigger and bigger. And actually that merger is actually happening all the time. Our own Andromeda galaxy, that's our neighbor, is coming very fast towards us, and one day they will merge together to create even a more beautiful nightlife. Hopefully humans are still there to enjoy it. And then look at the protostars, through the dust, to the nebula, inside the nebulas, how the new stars are born, how the planetary systems evolve around the stars, and how those debris field around the stars turn into a planetary system like ours. So next two videos will go over that.
The places where stars and planets are born are among the galaxy's most beautiful locales. These cosmic landscapes change as new generations of stars light up and disperse their birth cloud. But the youngest stars seen here are already perhaps 1 million years old. Hardly toddlers.
Stars and planets form in the dark, inside vast cold clouds of gas and dust, such as these pillars imaged by the Hubble Space Telescope.
The dust is so thick we can't see the infant stars inside, at least not with visible light.
With infrared light, Hubble can see through all but the thickest dust. Yet it's in those dense knots that the youngest stars are forming.
To peer inside them, astronomers need the James Webb Space Telescope.
With a mirror larger than Hubble's and performance optimized for the infrared, Webb will give astronomers their closest look yet at stellar birth.
We're flying through a computer model that represents astronomers' best ideas about the star formation process.
Reddish colors indicate thicker dust. The temperature, less than 400 degrees below 0 Fahrenheit.
Or less than 240 degrees below 0 Celsius.
That pinwheel ahead is a protostar, perhaps 10,000 years old. Protostars arise when a dense knot of dust, less than a light year across, collapses. But the details of the process are not well known.
Elsewhere in the cloud, another protostar is preparing to build planets. As the cloud that created the protostar collapsed, it flattened into a disk. The disk we see here is 600 times the size of Earth's orbit around the Sun.
If placed in our solar system, it would extend far beyond the planets.
In this computer model, the disk continues to accumulate gas and dust from its surroundings for thousands of years. Eventually, the disk fragments, producing dense, bright structures. These may become sites where giant planets form.
Later, during another phase of construction, smaller Earth-sized planets may take shape.
At least, that's what scientists think happens. It will take the Webb telescope's keen infrared eye to see what's really going on in the cold heart of stellar nurseries.
Planets begin as dense knots in a cloud of gas and dust, swirling around a young star. But how do they go from something like this to something like this? With the James Webb Space Telescope, astronomers will be able to study how planets come to be and how they change as they get older. After centuries of searching, astronomers are finding exoplanets just about everywhere, ranging from giant planets with masses much greater than Jupiter's to worlds only a few times more massive than Earth. But where do the planets we know best fit into the menagerie of worlds astronomers are finding? How did our solar system come to be the way it is? Why is Earth a balmy, water-rich world? And are there others like it elsewhere in the galaxy? These are the kinds of questions astronomers will address with Webb. For planets that pass directly in front of their stars, Webb will search for chemical fingerprints, identifying atmospheric gases like water vapor, carbon dioxide, and methane that absorb specific wavelengths of the star's light. Webb will also study the dusty disks where new planets form to reveal how the chemical compositions of younger and older disks change with time, and identifying how these changes are reflected in the planets we find. Such studies will be revolutionary in their own right, and by applying Webb's capabilities closer to home, astronomers will better understand planetary systems.
So to do all those things, these are the four instruments that are installed and built inside the James Webb. Three of them are optimized in the near infrared, and then one of them is optimized all the way to mid-infrared, anywhere from 0.8 to 28 microns. So with these instruments, hopefully it will really widen up the window that we can study the universe with. The near cam also has a coronagraph, what we call a coronagraph. So imagine you try to take a picture of a planet that's revolving around another star. Stars are very, very far away. Planets are very close to the star. Star is probably 10 billion times brighter than the planet. So how do you take a picture of a planet so close to such a bright object? Just imagine a firefly flying next to a searchlight. If the searchlight is off, you can probably look at the firefly. But when the searchlight turns on, you can no longer observe the firefly. So a coronagraph, what it does, which right now we still haven't perfected the technologies, to very strategically block out the light from the star enough so that we can actually take a picture of the planet itself. So that's a coronagraph technology. It's kind of a trial basis to see how well it can work. So James Webb has one of those capabilities on it. So hopefully we can actually image. We have never imaged an actual planet. We only discovered thousands of them by just observing its effect on its surrounding. The near spec also is basically a spectrograph. Like the video said, how do we tell if there's a planet and what it is made of, or even if a star, what the star is made of? And there's a technique or tool called spectroscopy, which is you take the light that's coming from there and you spread it into the range of wavelengths that it consists of. So if an alien being, or even us, take a sunlight that's coming through our atmosphere and do a spectroscopy, put a prism in front of it and have it spread out, break out its various wavelengths. In those wavelengths, you will see the signatures of all the elements that are in our atmosphere, because each element has a certain frequency of light that they would absorb, and so you won't see that intensity of light in that wavelength. You will see dips. So by understanding what each element does to the light, you can really tell what that object is made of. So even though we cannot see a planet, but if we're fortunate enough that there is a planet around a star, eventually it will go in front of the star. And again, if you're lucky enough that that passage of the star, a planet is right in sight of our satellites, we can take the spectra of that light if that planet has atmosphere, and we can study what its atmosphere is made of. So we can tell, what the abundant elements are in there. We also understand by looking at our atmosphere, if there is life on Earth, what signatures does the life produce? There's water vapors, there's oxygen, there's methane, which is a very big indicator of biological activities. So we can look for those kind of elements in the other planets to see if there is any chance of biological activity in those planets. So a spectrograph is a very important instrument, but it takes a long time to look at an object and take its spectra because they're so far away. So near spec, we had yet another technology we had to develop using the micro electromechanic machines, very, very tiny machines that can create a tiny slit in front of about 100 objects that are in the focal plane of James Webb. And a slit, of course, creates the spectra. So James Webb can take a spectra of 100 objects at the same time. So it really is very, very efficient, and it can do the science much, much faster than what Hubble could do. So these are some of the instruments that are out there on the James Webb. So let's now move into the engineering challenges. So I'll just talk about two challenges that were actually caused by the third limitation. The astronomer said we need as big a mirror as possible. The size of Hubble is not enough. Hubble has a limited IR. So if you were to make an IR instrument, we need much bigger telescope so that we can see much, much farther. It can collect more light, more faster. And of course, they needed, they wanted 10 meters and whatnot. We didn't have the technology or the funding. So we negotiated, 6.5 meters. But then it needed to be at cryogenic temperatures. And I'll talk about why that is. And that created to figure out how to cool cryogenic temperatures, meaning minus 260, minus 270, 60 or 30 degrees centigrade. So how do we cool this telescope to that? So that created big structures to shade it from heat sources. But the problem was the launch capability. Just the mirror itself is 6.5 meters, but the biggest rocket we had can only fit 5 meters of a diameter. So we had to build these huge things, break them up into like an origami, to fold them into smaller pieces so that it can fit into the rocket. So these three things kind of drove all the engineering challenges and the technology development that we had to go through. So let's talk about the primary mirror. Next slide. Next slide. Next slide. So this is a comparison between a Hubble mirror, which is 2.5 meters, versus what we needed to build for James Webb, 6.5 meters. James Webb, most perfect mirror we've ever built. The Hubble mirror is the most perfect mirror we had ever built. If we had Hubble sitting in Washington, D.C., and there was a firefly in Australia, it could take a picture of that firefly. But then it's a monolith. It's a single piece of glass of 2.5 meters, very finely ground and very, very thick so that it could sustain the launch environment and does not get warped by the temperature changes in space and whatnot. It's very, very heavy. So of course we knew how to build this one, so why not build same technology mirror, 6.5 meters. Two issues: we couldn't fold it to fit in the rocket, and secondly, it'd be so heavy that that rocket won't be able to lift it. So we had to think about how can we make this 6.5 meter mirror that is light enough, strong enough, and foldable enough. So we went to what we call the segmented mirror approach. So just think about it. Build a 6.5 meter perfect mirror. You chop it up. So you put each of those chopped up pieces on a frame that can fold so that you can actually fit it into the rocket. So it's kind of that, but what we did was we built 18 single mirrors that can be installed rather than building one and cutting it up, which didn't make any sense. So we built 18 mirrors. Each and every one has a certain portion of the total prescription of James Webb. And so we will place it so that once it's folded back up, it will act like a single mirror. So segmented mirror technology and what material to use and how to make it very, very thin and lightweight yet strong took a lot of years and a lot of money to figure that out. So now the 6.5 meter mirror altogether, including the frame and everything, is no heavier than the Hubble mirror. Next slide. And this is what it looks like. The total fully deployed mirror. You can see how big it is compared to the humans in the clean room. Next slide. Then we had to figure out we need to test these things. We cannot just build them and throw them up in space. We got to make sure it's going to work because there's no way to go and fix anything. So we needed big enough chambers that will take this mirror. So fortunately, we had an Apollo program, that had ended in late 70s. It had huge chambers, but they were used for different reasons. So we had to modify all of those chambers to our needs. And this is the mirror inside one of those chambers is being tested for thermal environments and also for prescription and all. Next slide. This is a portion of it, and this is how it looks like when the frame's folded up. And so it's in 3 segments, the central segment and 2 wings. So when you do that folding, it can fit into the rocket. Next slide. But how do you know that we have 18 different mirrors? We put them together. It's going to shake up during launch. It's going to unfold, and there's no reason to believe that they will remain in the position that we first installed them. So how do we have the capability to make sure that we can align those mirrors if they are unaligned? So that was yet another technology we had to develop called the wavefront sensing and control. And next video will talk about how that works. But basically, you think of when the mirrors are folded up, you basically have 18 different mirrors. If you take a picture of a star with 18 mirrors, each mirror will put the focus of that star some point outside of the focal point, because they are out of alignment. So we had to do reverse engineering to say, okay, take this image, it's so far to the right or the left of the focal center. So how do we move this mirror up, down, left, and right to bring that image to the center? And next slide. So to do that, we have actuators at the back of each of those 18 segments. And the step is very, very small. It's 1/10,000th of the size of a human hair. Each step can move the mirror by that slight amount, left, right, up, or down. And there's some actuators in the middle, so if the shape or the prescription has changed, we can actually pull or push in the middle of the single mirror to change its shape. So the next slide shows how we do that. Next slide. So each and every mirror actually has to go through 18 different steps to be formed, anywhere from digging for the material, beryllium material, which we finally figured out what material to use. So next video quickly shows you what all the steps each and every signal mirror had to go through before it could be launched.
Our most powerful window in the universe is nearing final assembly. A 21-foot diameter segmented array of mirrors is the heart of NASA's James Webb Space Telescope. This powerful successor to the Hubble Space Telescope will allow humans to see farther into the universe than ever before. This Herculean effort has pulled together technical experts from across the nation. The Mirror Odyssey begins in a mine where the precious metal beryllium is extracted. Beryllium is the choice for mirror material because it is lightweight and stable at the cold temperatures of space. The beryllium powder is cast into 4-foot-wide hexagonal mirror segments. They are precisely ground and polished to a precision 1,000 times smaller than the thickness of a human hair. The mirrors are then tested to simulate the cold of deep space at minus 400 degrees Fahrenheit. Mirrors are next coated with a very thin layer of gold, which is needed to efficiently reflect infrared light to the telescope's cameras. The mirrors are then vibrated to see if they can survive the rigors of launch. At present, the mirrors are nearly completed. They are ready to be positioned on a giant skeletal frame. Cameras and other instruments will be added to the rear of this backplane. The telescope will then be rolled into the giant thermal vacuum chamber used to test the Apollo lunar spacecraft. After that, the 2-story high optical telescope assembly will be attached to a tennis court-sized sunshade designed to deflect heat from the sun. The telescope's gold mirrors will be used to seek our cosmic origins by seeing earliest galaxies and perhaps detect the first glimmer of life on an alien world.
The challenge was temperature control. So, like I said, the telescope needed to be at cryogenic temperatures. Why is that? It's an infrared telescope, right? So everything that it's looking at is coming from a distance. It's in infrared light. But infrared light is emitted by anything that has temperature. I'm emitting infrared light. You guys are emitting infrared light. And if the telescope is warm, let's say it's launched at room temperature, when it's in space, it's going to get heat from the sun and all that. It's going to have a certain temperature. And it's going to emit infrared light as well. And so how do you know that the image you're looking at is the telescope's light or is it image that's coming from the universe? So to reduce the confusion, you need to figure out how to eliminate the infrared signal that's coming out of the telescope. And therefore you cool it. You cool it so low that the signal to noise ratio is large enough that you can now actually image the thing without getting polluted by the temperature of the telescope. But how do you cool these huge things to these low temperatures? Of course, we could put refrigerators and cryo coolers and whatnot to cool various parts of it, but that adds complexity, that adds weight, and all those issues. The other easy approach is to make use of what we have in the universe. And we know that the universe, this space, is the perfect heat sink. It's at almost 0 degree Kelvin, 4 degree Kelvin. And so we can reject heat from the telescope into space and let it cool down passively. You can do that, but then of course there is sunlight hitting it, so it's going to heat it up again. So the only way to get to that temperature is to figure out how much sunlight you got to block from hitting the telescope, or even the Earth reflection or the moon reflection hitting the telescope, and let it radiate so that when the equilibrium occurs, it's at that temperature. So, next slide. The solution is actually very simple. You put a sun shield between the telescope and the sun, or the source of heat. And we decided, okay, we need 5 different layers, and I'll talk about how they work. Create a sun shield, and Next slide. So there are 5 layers. This is how this works. The sun is coming from here. The telescope is on this side. Sunlight is about 1400 watts per square meter flux at that orbit. And so it hits the first shield. Most of it is reflected because of the coating on the shield. But of course, the shield gets hot. So it starts generating infrared light, which gets bounced off by the next layer out to space, and so on and so on. So by the time the last shield is there, it only allows out of the 1400 watts per square meter to maybe microwatts. And so only the microwatts of energy from the sun is hitting the telescope, and it's radiating its own power that's creating the electronics and whatnot are heating up the telescope. They get radiated into space. So the concept is very simple. The issue is the size. To protect the whole telescope and allow it to look left and right while still protecting from the sun behind, it needed to be a certain size, and the size turned out to be almost size of 1 tennis court, and then 5 of them. And of course, those don't fit into a 5-meter fairing of a rocket. So the technology challenge was how to roll these things. These are very, very thin materials. I don't know if you ever tried to pull out a saran wrap or something to cover your food. It always gets screwed up, churmur ho jata hai kuch, so it never comes out smooth. So how do you make sure that these things can be rolled in when we launch, and after launch, it comes out smoothly without getting stuck and so forth. So that's where the challenges was. So the next video shows you how many humans and how many hours it took to test the rolling in and out of the sun shield. And so the next slide. So the telescope, when it's fully deployed, looks like this. And when it's in the rocket, it looks like that on the right. Next couple of slides kind of show you a little bit more. Next slide. That's in the rocket, how it's fitting in the rocket. The next slide. So the next question is, where do you send this telescope? That's the most optimum orbit for it. Of course, Hubble is in the low Earth orbit. It's only 500 kilometers above the Earth, and it's going around the Earth at 18,000 miles per hour. But of course, it's getting the heat from the sun, it's getting the heat from the Earth and the moon and so forth. So we have different requirements for Hubble, so it's okay to do that. But James Webb couldn't do that because the sun shield would have to be so complicated and articulating to track the sun. So we know that there are few orbit points discovered by Lagrange, that any two massive bodies create 5 Lagrange points where you can, in the simple terms, think of it that the gravitational forces of the two bodies almost become equal to each other, and so there's a very stable point. There's no gravity wells anywhere near that point. So if you can orbit something on the Lagrange point, it will stay there with very little fuel required to maintain the orbit. So we decided to send James Webb into Lagrange point number 2, which is 1.5 million kilometers away from the Earth. And the next video will show you how that works. Is basically the Lagrange point moves with the Earth. And of course, the telescope is always facing away from the sun. And as the Earth goes around the sun, so does the telescope. And so it has view eventually to the 360 degrees of the universe. So over the course of 1 year, it can observe the entire universe to a certain limitations of moving left and right or up and down, so that it can avoid the sun. So I'm very happy to announce that James Webb has actually reached that point. All the things have been deployed, mirrors been checked out, it's all working beautifully. And so I think pretty soon it'll start doing the science that we hope it will do. Next slide. Of course, Hubble is still out there. It's been there for 32 years, and we hope it'll continue to work. Nothing right now is wrong with it. All the systems are working. Some of them are, of course, on their redundant side, but still working fine. So together with visible observatory and a far mid-infrared observatory, I think we have opened up the window to the universe to a new eyesight. And we can't wait to see what it discovers, what questions it answers. And we're also sure that we'll also find some new mysteries that we don't know the answers to, and we're going to count on you kids here to answer those questions when you grow up. So that's all my presentation. I appreciate your attention. Thank you very much for attending. Happy to answer any questions. I'm glad that Parvez Saab is here in case you ask very difficult questions, and I'll defer them to him.
I have a couple of questions.
Sure.
These mirrors, are they flat or are they curved?
Yes.
They're obviously concave mirrors.
Right.
But with different radii of curvatures. Right. What does one lose by having these 18 segments? There certainly is some loss over there.
Yes.
Of quality. So how does one quantify that loss?
So that's why the shape of the hexagon was picked, because that leaves very little blank space. And so infrared being a little bit longer wavelength, it doesn't create that kind of an issue. But again, that loss has to be calibrated out of the system after you do the observation. But that's the best you could do. You could not build a single mirror, but you're right. If you assume all of them are together, they together create a single prescription. So each and every one has a certain different prescription to make the final prescription.
How can you look at 18 different objects at the same time? As you said, you can...
It looks at only one object with 18 mirrors, same object.
Okay, but you said we can do simultaneous spectroscopy.
Yeah.
So how do you do simultaneous spectroscopy?
Oh, yeah. Okay. So the focal plane is pretty large. So when James Webb is taking an image, it's taking an image of your target, but it's also taking the image of all the things around it. So if you've seen the first image that's come out, it's of course looked at a star, but you can see all kinds of galaxies in the background. So the detector size is pretty big. So you get ancillary data. So then you can put a slit over each and every object that you, up to 100 objects that you want at the same time. So the astronomers, if they're looking at some systematic issues, they would look at the bigger picture and then do spectra of all of them. So in that science mode, it looks at a lot of different things. But for the fine tuning, they just pick one target for the 18 mirrors.
Okay. One last question. Is radiation pressure of photons from the sun a problem in making the shield?
Yes.
For your the solar shield?
Right. So if you remember in the deployment video, the first thing that comes out before the shield comes out is a damper that fights the solar pressure and equalizes it. So yeah, it's definitely a major problem that you had to face.
My question is about that how you have zero gravity out there, and you have to test all your equipment on the ground. So what challenges you faced while doing that, or what criteria you used to have that thing qualified?
Right. Very good question. Certain things you don't need to worry about gravity or zero gravity. The only thing we have to worry about is the delicate operations of the sun shield. Everything else, we're not moving. We understand zero gravity. So in the mechanisms and all, you can actually calculate that out or remove the gravity in your simulation and what. In some cases, of course, you can't create a zero gravity for this entire sun shield. So what you do is make replicas or equivalent smaller models that you can create. You can string them in a way to create zero gravity and test those, and then extrapolate that to the whole shield. And then, of course, what you learn, you can simulate. You verify your models with the smaller objects, and then you can increase the size of your model to calculate what happens. But then you add a safety margin of safety on top of that, because you never know that you've got everything.
When we are expecting it to complete all its trials and the first image will be available?
I believe that it's just finished this fine-tuning of the mirrors, but I think it might take a little bit longer to cool down the instruments. You got to calibrate all the instruments as well. So I thought that they were saying about 6 months after launch. So it was launched end of December, so 6 months from there, hopefully you will start actually using it for science. So again, the way science works is, of course, you have a science team that went through the project in defining requirements and whatnot. So that science team has the first dibs on the science data, and they will collect the data. They have a year to do whatever they need to do with it, to publish papers and whatnot, and then that science gets published, and then the data becomes available to the rest of the world.
First of all, thank you for the wonderful presentation. My question is, how much does this telescope costs? Can you explain it in simple terms? We can understand. Yes, cost.
Yes. So let me give you the history of the cost. When we first decided to, what happens is every 10 years we get the science community together to say, okay, what do you want to do in the next decade? What questions have we answered for you? What questions are still there? So every 10 years they come up with, and so I think in the 1980s, decadal review, they said we need James Webb. And so the NASA administrator at that time said, okay, you can probably build it in $500 million. So we started the project. Of course, you have the different phases. You got to phase A, you got to do trade studies and whatnot. And we said, no, I don't think 500 million is enough. It'll at least take $1 billion, because when you look back at the history of Hubble, 2.5 meters cost almost $2 billion. So how can you say, 6.5 meter will be $1 billion? Are you nuts? And we said, no, we have experience. Of course, we don't have any experience. Everything we're building is building for the first time, and the technology development. So in the end, it cost growth because of technology, but also there's the efficiency of how well you are given the funding. So a lot of times the Congress doesn't give you the funding, so you have to slip the mission, and of course it costs more. So in the end, it cost $10 billion.
So I have read somewhere that how well the launch goes, it makes the time span that it's going to remain up there.
What's the life expectancy of the James Webb?
Yeah.
Yeah, so then that can be answered in two different ways. One is from the cost perspective. So if you want to have it work for 1 year only, you don't have to worry about too many failures, because you can think, ek saal ke liye to chali jayega. But the longer you go, the more redundancy you have to have. You have to do all kinds of analysis to see how long will this computer last in the radiation environment. And if it's not going to last 5 years, then you got to have a backup computer and so forth. So at a certain point, you got to stop and say, with this kind of $10 billion, I can only make it last for so long. So the official design life, which we call design life, so what do you design it for? That it should not fail no earlier than that. That's 5 years. And the consumable, James Webb, like I said, the doctor said, there's a solar pressure and the orbit gets pushed around. So every once in a while we have to adjust the orbit. So there's a fuel that's required to do that. And so we figured fuel is the least expensive, lowest mass. So let's put enough fuel so if it lasts for 10 years, it should have enough fuel. So the fuel consumable life is 10 years. The design life is 5 years. But we surely predict that as we start to operate it, we'll figure out how to operate it more efficiently, like we have done with Hubble. Hubble life was 15 years, and it's now 32 years. So we hope that it can last much longer than 15 years.
I have a question, sir. The way Dr. Carl Sagan motivated the community inside the NASA, that Voyager should work like way beyond the expected life. Because you work there, is there some expectation of your science community to work James Webb for a long time?
Of course, they would want it to stay there forever. Of course, they would want, lifetime. They would never want anything like Hubble or James Webb to not work anymore. But then you got budget realities, not for the designing, but to operate. Like it takes $100 million a year to run Hubble. That's probably the same amount for James Webb. So at certain point, either I don't expect it, but you could overrun the utility of James Webb. For example, if you want to image exoplanets, James Webb cannot image, so you need bigger telescopes. So the current decadal survey that finished, they want a bigger telescope than James Webb with the whole spectrum all the way from visible to far IR capability. So every 10 years they're asking for more and more, and of course that technology will continue. But yeah, so the lifetime is actually limited by physics of how long things can survive in radiation environment, and then budget.
So my question is about, you said we have to stay focused to take the picture, like you explained in the Hubble telescope. So how do you keep it focused on one plane when it's constantly moving? Like Hubble is moving very fast. So how do you stay focused for several days or several weeks?
That's a very good question, and that's a huge technology challenge we had for Hubble. It's easier for James Webb because, of course, it's not moving as fast, and it's moving in one plane, so it can actually keep one thing in focus, and I'll show you how it does that. It's more difficult for Hubble because it's going 18,000 miles around the Earth, so if it's going if this is the Earth and is observing somebody there, it has to go across the Earth, reacquire, come around, and it's... So we had, for Hubble, had to develop very, very high sensitive gyroscopes and fine guidance sensors. So what happens is when a scientist wants to observe that object, how does Hubble know that it's actually pointing at that? So the scientist has to figure out, okay, to do that, there are two guide stars in my own neighborhood that if I can lock onto those, then I'm locking into the target. It has to be two, but if it was one, I could be rotating around that star, and so the two minimum guides. So those guide stars are very, very highly sensitive detectors that take the light of the star and then keep that star in that center of the guidance. So if the Hubble moves, the gyroscope tells you how it's moving. It sends a signal to bring that star back into life, into the center, and move the reaction wheels. And so that's how it stays focused. And so the requirement for Hubble, if it's to take deep images, then you got to stay focused on that object. So again, imagine a clock. It has 360 degrees, right? So 1 minute out of that has 60 seconds, arc seconds. And so Hubble was required to not be disturbed by anything, whether it's solar wind or heat expansion and whatnot. If he's locked into an object, it should not move more than 0.007 arc seconds over 24 hours. And we achieved that.
Sir, it must have some blind spots when, like, in the 360-degree circle.
Yes, so unless it's looking way up, all it needs to do is do this. But it's going like this, it's more complicated. It goes in front of the Earth, it loses the target. When it comes around, it has to reacquire. So that's why the efficiency of science is, the design efficiency was like 30%. You got to be able to do science 30% of the orbit time, but we have actually figured out how to make it so it's up to almost 60%. So James Webb is same idea.
The question was about the alignment of the mirrors that's performed. What was the residual error that you achieved, that the convergence error at which everything was fine?
I don't know the answer to that. They just finished that, and all I know is that they're excited, they're thrilled that it's gone better than what they had expected. So.
All right, sir. It's pretty evident looking at the telescope mirrors that probably it's gold-plated, if I'm not wrong. Is that correct? So what's the physics behind that particular?
So gold turns out to be the best, most efficient reflector in the infrared.
You mentioned the solar wind. So how do you get around the effects of that in this?
Right. So we have a damper on the opposite side that. Somehow, I don't know the exact details of it, but there is a damper that you have deployed so that counteracts. If the solar wind is coming this way, the damper is also getting the solar wind in a different direction, so it kind of balances. But still, like I said, we have to adjust the orbit every once in a while.
Once in a while?
We don't know, we'll yet to find out, but not too often because of the stable orbit that it's in. So that's why I think the fuel that we have will last for 10 years. It's only there to fight the solar wind disturbances and stuff.
Assalamu alaikum. Wonderful presentation, mashallah.
Thank
and
you,
it educated me a lot. There are lot many actuators, lot many mechanical arms, all those. From where do you get the energy? All from solar, or you have some batteries over there, and there must be some hydraulic oils and all those things. Are there? And
yes.
How would you manage all those things? And the second part of the question is that after it has expired its life, would you have the capacity to recover it, or it will go astray? Thank you.
So the power source is solar, and it's always facing, the telescope's facing away from the sun, but the solar rays facing the sun. So it's constantly getting the sun, and since there's no earth to block it, there's really no need for batteries. We have batteries to take care of the early launch before we can deploy the solar panels. So the batteries are there during the launch phase to take care of the housekeeping and deploying things that we need. But I think the batteries are there as a backup only. We don't need them right now. The solar power is the main. Of course, it has lubricants and whatnot. They had to be added, but they had to be hermetically sealed so they don't escape. And of course, eventually they will run out, and that's how the life will end. It is 1.5 million miles away. We don't have the technology to send anybody, or there's no utility to bring it back, unless one concept we're working on is generally in general satellites, robotic refueling, where we can actually bring those satellites closer to Earth, where we can actually send even humans and then resend them back. But then again, that's a very complicated and expensive proposition. But as a rule, as a agreement between all spacefaring countries, we are no longer allowed to leave junk in space. So every time we build a satellite, we have to design its disposal, because they won't let us launch if we don't tell them how we're going to get rid of that satellite safely. So for the case of James Webb, we will just let it drift off into deep space, and it'll be out of the way. Other satellites, for Hubble, for example, we have to intentionally crash it into the ocean or park it into a graveyard orbit, or actually send it away, also like James Webb, but it doesn't have any fuel, so we'll have to actually build another robotic rocket that will go up, grab Hubble, and then either bring it down or send it up. But that hasn't needed yet, thankfully. It's still working.
Sir, as you mentioned that universe is expanding day by day, is it just the distances between every planet is expanding, or the mass of planet also expanding day by day?
When you say mass of the planet?
Yes.
No.
I think it's radius or diameter.
No, just each and every, the local, correct me if I'm wrong, the local environment is there, but things, let's say galaxies, clusters are moving away from each other. So think of it as a balloon. There are objects on the balloon. If you blow into the balloon, everything on the balloon is moving away from each other. So the space is expanding.
By that time, as we can see too many far of a light years through this telescope, but as the time passes, can we see through that distances, or distances become smaller and smaller by time?
No, I would say distance get bigger and bigger. Distance become bigger and bigger by time. So things will get farther and farther away. So eventually we probably may not be able to see some of those.
सर मेरा सवाल तो बहुत सेंसर के बारे में है ना, जो टेलीस्कोप के आप जो सेंसर यूज़ कर रहे हैं ना, इस किस टाइप ऑफ सेंसर आपने यूज़ किया है, क्योंकि जो सन का टेम्परेचर है ना वो उसको एक्सेस कर सकता है, उस सेंसर का नाम बता दें. और
I'm sorry, I don't remember it's probably gallium arsenide or something like that. I'm not too sure. So, and temperature, of course, has to be much, much colder. It's cryogenic temperatures, like minus 230 degrees or so.
सर और सेंसर का लाइफ टाइम कितना है जो यूज़ किया है? How many year?
We hope it will last 5 years at least, but there are 4 instruments, so there's a lot of backup in each of the instruments to continue the science. But I don't know the exact answer. I'm sorry.
Okay, thank you.
About the communication with this telescope. So how are we communicating with it? And do we have the ability to send the commands? And
Yeah, absolutely. It's just like you control your TV now. You push a remote control. It's just far away, so it takes a few minutes. You just can calculate, the sun.
So just as an example, if you want to download some image, how long it takes?
So again, speed of light, 1.5 million kilometers. I would say a few minutes only. Okay. And so the way it operates is you send the commands for the whole week, and it starts executing. And it has probably when the ground stations come into the view, you can downlink the data, and that's how it works. So it's nothing unusual about the communication, not that far, not like Voyager and things on Mars and stuff. Thank you very much, everybody. I really appreciate your time spent with me today. I really thank you.